Good morning, everyone. My name is Samuel Chen from Wells Fargo. Today, I'm excited to share our recent work titled Learning to Measure Quantum Neural Networks in collaboration with Brookhaven National Lab and Seton Hall University. This work explores a relatively under-discussed yet crucial element in quantum machine learning, the role of quantum measurement. Here is the outline of my talk. We will begin with the motivation behind this work, followed by an overview of variational quantum circuits, also known as the quantum neural networks. Then we will explain the concept of quantum measurements and how we can optimize the measurement operators themselves. We will wrap up the results and concluding remarks. Quantum machine learning, or QML, seeks to harness quantum computing to tackle complex learning tasks, such as classification, speech recognition, time series prediction, and more. One of the major bottlenecks in quantum machine learning today lies in its rigid design choices, especially in how quantum measurements are performed. Most quantum machine learning models rely on predefined or fixed observables or measurements, such as Pauli X, Y, or Z matrices, which means that the model output is bounded in a limited range, typically -1 to 1. This restricts expressivity and makes it hard for the model to adapt to real-world or complex data sets. Our key idea is simple but powerful. Make the measurement operator itself trainable. Just like we train the parameters of quantum gates such as those rotation angles, we also learn the Hermitian matrix used in the measurement. This creates an end-to-end differentiable model that learns how to measure or project the quantum system, not just how to encode or how to rotate the quantum states. As a result, the model gains the flexibility to adapt its output space or range to the task at hand. In our numerical simulation, we observed significant performance gains, over 10% improvement in synthetic datasets such as make-wounds, and up to 96% accuracy in real-world speech recognition dataset VCTK. Before diving deeper, let's briefly review what is a variational quantum circuit or quantum neural network. This circuit is also called a parameterized quantum circuit. These circuits are the backbone of most quantum machine learning models, and they are quantum circuits with learnable or tunable parameters. These parameters are subject to iterative optimization. There are at least 3 major components in the variational quantum circuit. The first is the encoding circuit, U of X, which will encode the classical input such as the speech signal, the pixel values, etc., etc. And the second part is the parameterized circuit, V of theta. Here, the theta represents the trainable parameters for the rotation gate or rotation angles. These are very similar to the weight and bias in the classical neural networks. And finally, the measurement part. Usually, those measurements are fixed observables, say fixed Hermitian matrices. Commonly used choices are Pauli X, Y, and Z, observables. So during the measurement, we usually choose an observable. For example, poly Z matrices is the commonly used one. We can compute the expectation value of this quantum system and the observable. For example, Z is observable here. The final output of a VQC is often a vector of expectation value across different qubits. For example, if you are performing a classical classification task and you have, say, n class or n labels, then usually you can measure n qubits, and you can perform the measurements on those n qubits. So you can calculate or measure the system to get the expectation value of each qubit. Given a quantum system, you will, if you prepare the system once and you measure the system, you will get discrete values. For example, if you measure the Z observable, then you get either -1 or +1. But if you measure the system multiple times, then you get the expectation value. You will get the expectation value lies in the range of -1 to +1. So you can interpret these values as the logits or probability of different class. Once you get these quantum function outputs, you can calculate the gradient of quantum functions via parameter shift rule. It means that if you have a quantum function and you want to calculate the gradients, so given a data point and a particular parameter that you want to calculate the gradient, you will need to run 2 circuits. So what exactly is a quantum measurement? It's the process of extracting classical information from a quantum state or a quantum system by applying a Hermitian operator or a Hermitian matrix. It is also called an observable. The result is one of its eigenvalues, and the average over repeated measurements give the expectation value. You cannot measure the quantum system many times. So in order to get the expectation value, if you are running the experiments on a real quantum computer, then you will need to prepare the system several times and you apply the measurement. That's the only way that you can get the expectation value. In quantum machining, the common choice is still the poly Z matrix, but this choice severely limits the model output range. What if we allow the measurement matrix edge to adapt and learn like a neural network weight? Here is where we introduce our core technique. So here is the definition of a Hermitian matrix. The Hermitian matrix satisfies the condition that B equals to B adjoint. So this condition requires each matrix Bij equals to its complex conjugate. Consequently, a Hermitian matrix can be generated by n squared real parameters. Given this knowledge, we can parameterize the Hermitian by just some real coefficient or parameters. And this matrix acts as the actual observable in the final measurement. And we can compute the gradient not just with respect to the rotation angle theta used in the variational or parameterized circuit, but also with respect to the observable entries. So here is the mathematical representation of this differentiable optimization of quantum observables. As we already mentioned, the Hermitian matrix can be parameterized by n square parameters. Here n is 2 to the power of n, where the lowercase n represents the number of qubits. Here we can expand the Hermitian matrix by using the basis Eij. Eij is the indicating matrix with only one non-zero entry at the location I and j. Once we get this representation, we can write the expectation value as this. So we put in the actual observable as sigma I of I from 1 to n and j from 1 to n, and then we expand all the Hermitian. We expand this Hermitian matrix as the parameter Bij times the basis Eij. We can factor out those sigma or summation symbols out as this. Then we can have the total differential as this. Once we get this, we can perform backpropagation through the whole quantum system. Here is the result. We start with a classic toy dataset, make moons, which is from the scikit-learn. We experiment this dataset under different noise levels to explore the robustness of the proposed model. We also compared 3 different models. The first is the baseline, which is the standard VQC and fixed observable. For example, here we use the Z observable. And the other one is a bit advanced, so it is the VQC with the learnable observable, but using the same optimizer. It means that both the rotation angles in VQC and the parameters for the Hermitian matrix are optimized by the same optimizer with the same learning rate. The third experiment setting is VQC with learnable observable and separate optimizer. It means that the parameters of VQC and learnable observables are optimized by different optimizer and different learning rates. So as we can see, the VQC with learnable observable and separate optimizer reach the best accuracy and the lowest loss. However, the original setting, the standard VQC with fixed observable, struggles to learn how to classify even this simple setting. And later we add more noise. So now we increase the noise level, and we can see that the standard setting degrades a little bit. However, the VQC with learnable observable and different optimizer keeps good performance. We further increase the noise level to 0.3, and we can see that the result is consistent with the previous 2 examples. Beyond the synthesized dataset from scikit-learn, we also test these results on the a real-world speech recognition task (VCTK) tasks. We use spectrogram features from 10 speakers and build a hybrid convolutional neural network plus VQC model. Again, we compare 3 settings. The standard VQC baseline achieves 70.6% testing accuracy. Our learnable observable boosts these to 76.8% accuracy. But when we use separate optimizer with different learning rates, the testing accuracy jumps to 96.3%. This shows that letting the model learn how to measure is not just elegant, it is very powerful. To summarize, we propose a framework to learn quantum measurements by parameterizing Hermitian observables. This explains the design space of quantum machine learning and removes the rigid assumption of fixed Pauli observables as in most existing quantum machine learning models. The model becomes more expressive and adapts better to complex tasks. Important results. We can achieve up to 96.3% accuracy on real-world speech recognition dataset (VCTK). Our key message is this. In quantum machine learning, how you measure is just as important as how you encode and how you design the parameterized or variational circuit in the model. In the future work, we aim to apply this framework to regression, time series, prediction, reinforcement, and privacy-preserving federated learning scenarios. Thank you for listening. Let's conclude my talk.